Okay, so welcome everyone to the Ambari talk on how to really scale your cluster and manage it when it really does matter. So again, thank you for the first day of the DataWorks Summit. So my name is Alejandro Fernandez, and I'm a PMC for the Apache Ambari project, and I'm also an engineer at Hortonworks, and I've been a PMC for the past 3 years and really work on a lot of features related to upgrade, service advisor, et cetera. And my colleague.
Hi, I'm Arvindan Vijayan, and I'm a senior software engineer at Hortonworks, and I've been a PMC for the last few days, actually.
So what is Apache Ambari? It's an open source platform that monitors and manages your Hadoop cluster at scale. It takes care of everything from alerts to security to stack upgrades, the whole works, right? And so I want to begin by doing a quick poll. So can anyone raise your hand if they have heard of Apache Ambari before? Okay, awesome. That's like 100% of the crowd. And who has actually tried it in a sandbox or production environment? Again, like 100% of the crowd. Fantastic. So the project is now 4.5 years old, and it keeps growing in size and scope. Actually, it is right now the second most active project in Apache, followed by Spark. And our community is growing. We have over 80 active committers and contributors. And just recently, we released Apache Ambari 2.5, and that had over 1,700 JIRAs of features and fixes. And last month, we released 2.5.1, which is a maintenance patch. And typically, we release a major version 2 or 3 times per year. So we're an extremely active community. So I want to briefly gloss over some of the new features in Ambari 2.5, especially how they relate to managing your cluster at scale and making it easier for Hadoop administrators. The first one relates to services. So there are features now for automatically starting services whenever your hosts are down. You can configure it on a per host basis. We also have a new wizard for a journal node that allows you to save the namespace and add more than 3 journal nodes. For security, we finally have password credential store and SpinEcho authentication. And on the core itself, I'll be focusing on this talk on skill testing up to 2,500 agents. The number isn't really important. What's important is how we're actually getting to this point of skill and stress testing Ambari, plus some features that Ambari can use to fix itself, check its database for consistencies, et cetera. Aravind will talk about AMS, so I'll let him go over that later. And there's a lot of new exciting work for the frameworks to make alerts better, to have Ambari native alerts, and also easier log rotation settings. So I want to talk about testing Ambari at scale. The model that we have today is you have 1 agent per VM, and that's a very simplistic model. But when we want to test, we actually want to try to see how we can optimize our resources by leveraging, say, up to 50 agents on a single VM. What that means is that in order to reduce the cost of testing and increase our throughput, right, we actually have to forget that we actually need Hadoop to test Ambari. Ambari just needs to generate enough traffic from processes that are running or get enough heartbeats, and that's how we're going to really get to test Ambari at scale. So we came up with a PERF stack for performance, and that can simulate actually running 50 agents per VM or more. And basically, we no longer have Hadoop running on these agents. Instead, we create dummy PID files to simulate the presence of services running. And Ambari server cannot tell the difference, which is great for us. And in the past, we tried a couple of different solutions, including Docker and Weave, and at the time, it wasn't very stable. So this is how we moved forward with that approach. And basically, we wanted to test different scenarios. How can you have, for example, some services that always pass, other ones that will present conditions like timing out, and other ones that will always fail? But we also wanted to introduce some realistic services that actually have lots of configs in history so that we can generate that same amount of data. So we added things like a fake HCFS, yarn, and HBase. But we also wanted metrics for Ambari server to look at the JVM, look at garbage collection, and potentially find slow running queries. So there's actually an Ambari metric system that's embedded into this performance stack. And basically, each one of these dummy services is extremely simple. All it does is essentially a no-op for commands like install and configure, because there's actually no bits running. And instead, we have the start command and the stop command manage a PID file to indicate whether or not that dummy service is running. And Ambari server, again, cannot tell the difference. So when we're actually testing at scale, we can spin up, for example, 60 VMs. Let's say each one could be 8 cores and maybe 16 gigs of RAM. And each one of these VMs actually contains, say, 50 agents. What this allows us to do is to test features ranging all the way from enabling Kerberos, also going through the HA wizards. We can test Stack Advisor much faster. We have all the alerts as well. The alerts that Ambari has today are either things like a port check or running a Python script. So we can still run Python scripts and fake them to produce whatever expected behavior we want. And actually, because there are 2 versions of the PERF stack, we can also do PERF testing for features like rolling and express upgrade, which is amazing because our customers are extremely critical of this feature. And if we can test it ahead of time at this scale, it's providing immense value to our users and customers. And last but not least, for any UI developer, it's extremely easy for them to get started doing development of Ambari, because they no longer have to understand the complexities of Hadoop. They can deploy this PERF stack and not have to worry about, I wasn't able to get my name node working, or it takes me 30 minutes to actually install the bits. So we remove all of this complexity and make it easier for UI developers to reproduce issues and work on new features. So here's a screenshot of it at 3,000 nodes. I was actually trying to get a demo for working for you guys, but instead I'll just show you a video at the end. And what were the actual outcomes of this when we released it in Ambari 2.5? So I just wanted to point out a couple of jurors that we fixed on both the server side and on the UI side to handle lots of traffic from agents, 2,500 at scale. So this is fantastic news for us because it really does make a difference, and we see these issues before users do. So I'll just show you a quick video. So there's a single command that I used to spin up all of my agents on GCE. And if you can see that, I'm providing a demo name to my cluster, how many, for example, agents I want. In this case, I actually did only 1,000 to make it faster. And this is going to start creating a very massive server that's got MySQL running, that's optimized for large scale. And it's going to create, in this case, 20 VMs, each one with 50 agents running on it. So I'm going to just fast forward for the sake of time for 1 second. So there was a lot of work to make each agent have essentially its own namespace. Each agent now needs its own log directory, its own PID file, et cetera. And essentially, you just use the UI and install the agents, and Ambari just doesn't know the difference. So here are some of those fake services installed, and I'm just going to fast forward. You pick all the hosts, and then in a couple of seconds, you get Ambari installing on all of these agents. And then once you're done, your cluster is up, and if everything is green, you can look at your alerts, and those are actual alerts doing stress testing on Ambari, and the goal is to make it be super fast. Okay, so I also want to talk about how to optimize your database for big data with Ambari. And this is more of a reference slide, but basically, if you're tuning your MySQL database or whatever other database you're using for Ambari, these are a couple of important points. Whenever you can, of course, try to have a solid-state drive for your database. make sure you're on the latest version of whatever the database type you're on. And it's also very useful to clean or purge your old Ambari history. Things like old commands, alert history, blueprint topologies, and even upgrades. And the rest of these are a couple of settings you can make in, for example, MySQL, depending on the number of hosts you have to optimize it. So some of these are for, sorry, these are Ambari properties. How many threads are going to respond to agent heartbeats, whether or not to enable alert caching, and we've had that feature available since Ambari 2.2, I believe, so it's pretty stable by now. And also how many threads to use for the scheduling of commands. So I also want to talk about upgrades and what's the most effective approach when you're doing this at scale. The olden days, it was a manual upgrade, and this could take weeks to orchestrate. You needed a lot of time coding using Chef and Puppet and whatever else you were using. And this is like the Fred Flintstone days, right? No one does it anymore, unless you have a very custom setup. So then we introduced rolling upgrades in Ambari 2.2. This is almost 2 years ago. And this is synonymous to refueling a fighter plane while it's still in the air, right? You're not taking any downtime, and you're upgrading your cluster one host at a time. The most recent addition to the upgrade family was Express Upgrade, which takes downtime. And this is synonymous to doing like a pit stop in Formula 1, right? So the upgrade process is actually really straightforward now because you can check all of your prereqs in advance. Make sure you have, for example, name node HA if you're going to do a rolling upgrade so that you do not incur any downtime. You can always install the bits side by side, so that saves you some time. And Ambari will actually install in large batches, and I'll show you guys how to change those values so you can get more parallelism out of the system. Next step is to actually perform the upgrade. That will do things like take backups, do the rolling restart, etc. And last but not least, you finalize and you're on the newer version. So there you go. So with a rolling upgrade, we go from the bottom of the stack all the way to the top, and we do one host at a time, and it's actually one component per host at a time. So we'll do Zookeeper, all three of those. Then we'll move on to, say, eventually core masters, which is name node and your, for example, HBase master. So each one of those, again, is one component at a time. So as you can see, a rolling upgrade, because it doesn't actually take downtime, is very time consuming. Okay? And if you ever encounter any failures, you can always retry a step. You can ignore and proceed if it's not a mission critical step. And the last option is to downgrade. Now compare that to an express upgrade, in which you do batches of 100 hosts in parallel, and you can actually change that number as well. You first stop your stack, taking backups throughout the way. You change to the new version, and then you start it in batches of 100 at a time, going from the bottom of the stack all the way to the top. And again, the same scenarios apply because it uses the same framework to handle the execution, the auto-retries, etc. So let's talk about time now. When you're using the rolling upgrade, if you have 100 hosts, it takes almost 3 hours. On the far side, if you have 1,000 hosts, you could be looking at 26 hours. Because it scales linearly with the number of hosts. Now, an express upgrade, it scales linearly with the number of batches, which is defaulting to 100 hosts at a time. So in this case, for 100 hosts, instead of 3 hours, you get 30 minutes. And for 1,000 hosts, instead of 26 hours, you get 2 hours and 20 minutes. So you get 11.4 times faster performance if you're using Express Upgrade on 1,000 hosts. And it's even more significant the larger the number of hosts in your cluster becomes. So this is also a reference slide, but Ambari has configs that allow you to change how many hosts you can install in parallel during the installation of packages. And also there are settings in the Express Upgrade XML files that allow you to control the batch size during the rolling restart commands. Also for large scale, you want to keep in mind that there are features for auto retries. If you're performing an upgrade during the weekend and it's unsupervised, you may want to enable this so that Ambari keeps retrying whenever it encounters a failure, either due to an intermittent host failure, some timing issue, whatever the case may be. So keep that in mind. Ambari is here to help you, and we, as developers, honestly have a lot of pride in features like this, and we really do care about them. So lastly, I want to talk about what's in the future of Ambari 3.0. There's a general theme about supporting multi-instance and multi-version. So making it easier for the users to be on the latest version of, say, Spark. How do you have 2 quorums of Zookeeper or multiple Kafka instances depending on your use cases? So that's going to come in Ambari 3.0. We also want to generalize what it means to be a service. A service could also be an assembly running on Yarn. So we're going to add a lot of support for doing that lifecycle management and making it easier to add other types of applications managed by Ambari. Patch upgrades is becoming increasingly important for users, and so they want a feature to be able to patch, for example, just data node in a maintenance or a hotfix, right? Or just some component like just clans, right? So this is going to install a minimal subset of the packages, and it should only be a minimal subset of the orchestration. So that's to have minimal downtime. In the future, we want to talk about other different design philosophies for upgrades. For example, how would you do it on a per host basis? And last but not least, we want to focus on Ambari HA. There are already ways to do this today using external tools, but we want to make this first-class citizen in Ambari. And with that, I'll hand it over to my colleague, Arvind.
Okay, thank you, Alejandro. So in this section, we will be covering the Ambari Metrics System, which is a very useful tool for monitoring your Ambari managed cluster. So we'll start with the basic building blocks in AMS, moving on to the various features which were added, and then the integration with Grafana, and then the distributed collector story, and eventually we'll move on to the future work. Okay, so Ambari Metrics Service was actually introduced in Ambari 2.0. So before that, we had a Ganglia, and the motivation to come up with an AMS was that there were some limited Ganglia capabilities with respect to scale and flexibility. We looked at OpenTSDB, but there was an there's a GPL license constraint as well as it needed a Hadoop cluster. So other than that, there were some requirements which we were looking for. One is the need for service level aggregation as well as time-based downsampling. And then the system must be pluggable as well as extensible. And we should be able to integrate with the alert system in Ambari so that we can have metric-based alerting. And then eventually, we should be able to perform analytics on a use case and the ability to scale past 1,000 nodes. And the system should be highly configurable with respect to the size of the cluster, like a 5-node cluster up to 1,000 or 1,500 node cluster. All these actually gave way to an Ambari metric system. So this is the high-level block diagram of AMS. The central component is the metrics collector, which is the API daemon responsible for the get and the post of the metrics, as well as it does all the aggregations with respect to the cluster as well as the time-based downsampling. So the sinks are the service daemons which actually push metrics to the collector. For example, a data node is a sink, a name node, the resource manager, all of these are sinks which push the metrics to the collector. The metric monitors are lightweight Python daemons which run on every host on your cluster, and they collect system metrics, and again, they push the data to the collector. So the data store which the AMS uses is HBase, and there are 2 flavors in which we use it, in embedded or distributed mode. In embedded, we write to local disk, and in distributed, we write to HDFS. So we have a Phoenix schema on top of the HBase, which is actually designed for doing very fast reads. And an important addition to AMS was a cool UI on top of all these metrics, is Grafana, which is supported from Ambari 2.2.2. Okay, going one level deep into what were the considerations done when we actually laid down the building blocks. So the schema. So we have a composite metric key, which consists of the metric name and the app ID. So the app ID is a data node or a name node from where the metric actually originated. And then the instance, if you have multiple instances of the same service. So all these together will give you the composite metric key, which basically are multiple Phoenix columns put together. So this helped us actually having automatic predefined region splits based on what services you deployed in the cluster, because we have a good understanding as to what will be the metrics which come from the various services on an Ambari cluster. So aggregations. So out of the box, AMS supports two types of aggregations. In the V1 version, we went with client-side aggregation, where we brought all the data into the metrics collector tier. We did manual aggregation and then wrote it back to the HBase through Phoenix. In the second form of aggregation, the server-side aggregation, we were able to use the Phoenix group by clause, which actually utilized the region splits for query parallelism. And third, we, with respect to HBase and Phoenix features which we use, we have the FIFO compaction policy, which basically makes sure that all cells with the expired timestamps are compacted. And this is very useful when we have raw data, which is TTL'd every 1 day. But before which TTL, we actually aggregate it to higher level data. The normalizer is a feature in HBase which does automatic region splitting and merging, so that if a region is not really used for reads, it actually merges less used regions together. The HBase timestamp support is where we can map a Phoenix column into the cell timestamp of a HBase region of HBase H file, such that if we have a where clause with a time-based filter, it will not look at cells beyond that time. All these were very useful in coming up with the initial design as well as performance considerations. So we have a high-level feature highlights in AMS. So a simple post API to send metrics to the collector, a good set of features in the get API where you can supply aggregator functions, you can have point-in-time data return, series support, of course, top-end metrics, as well as rate and diff support. And out of the box, we have two types of aggregation supported. One is the host-level aggregation, where a metric is aggregated across all hosts from which it is received, and also time-based downsampling. So the metadata API is another useful addition where it gives you some topology-related information as to where the metric is coming from, and in the Ambari managed cluster, what are the different apps in a host which actually send metrics. So the system is highly tunable. You can tune the rate of collection, what intervals you want the aggregation to be done. You can skip aggregation on certain classes of metrics, and also you can whitelist some metrics, you can blacklist some apps and whatnot. And eventually, we have a very useful abstract sink. So this abstract sink can be used by anybody who wants to write a sink to publish metrics to the collector. A lot of features come out of the box in that abstract implementation, and it will be a lot easier to get bootstrapped with that. OK, going one level deep into aggregation. So the sinks and the monitors send raw precision data to AMS. So it's about 10-second data which they send. The first aggregation which is done is across hosts. For example, if I have a memory-related metric coming from 100 hosts, we aggregate that metric across all hosts, sum, min, max, average, and this is stored as 30-second aggregates. Now we have two types of data, which are the seed data, and then we have time-based downsampling done. So you can think of every box in this diagram as a table in Phoenix we have, which stores different precision data. So we have 5-minute intervals, 1 hour, and 1 day, and all of these are configurable through your aggregator intervals. OK, so the get API is pretty straightforward. It has metric names and app IDs, which are the mandatory to what kind of metric you want. So the start and the end time are optional, because if they are not supplied, you just give the point time data, which is the last known value of that metric. The host names, if specified, is going to give you host-level metrics. If it is not specified, it's going to give you cluster-level aggregates. The instance ID is only used if there are multiple instances of the same app deployed in the same cluster. And the precision is if you want the data to be picked up from what table. So by default, we make our own back-of-the-hand calculation to give you the precision. For example, if it is 1 day, we give you the lowermost precision data. If it is last 1 year of data you want, we give in days. But you can specify the precision you want the data also. OK, so a cool addition to AMS in 2.2.2 was Grafana, where we contributed an AMS plugin, data source plugin to Grafana. So this leverages the get API, which was discussed last slide. So this is how our AMS Grafana plugin looks. And we can request host-level data or cluster-level data. We can request different positions, and we can request different aggregator functions like sum, min, max, average, and as well as rate and diff. All these are very useful, to try out different graphs and check out what the metrics look like. So one step in addition to the data source plugin was that we created a set of service dashboards, which are created by service experts themselves. So they really help us identify some problems in your system which are actually shown in metrics. So this is an example of a top-end dashboard with the top-end bar in the, all the way in the top of the dashboard. And this will really help us find out outliers. So for example, we have an issue on a cluster where HBase is writing to 200 data nodes. And the problem was that in one of the region servers, the load was unusually high, and the RPC call queue length was also very high. So it took a long time to find out what the issue was. But the problem was that one of the network cards in a data node was wrong. This could have easily been found using the data nodes dashboard, which we have, the top-end dashboard, using the packet round-trip numops metric. So this is how the operational statistics looks for AMS with respect to disk usage and the write load, what is required from the system by AMS. For example, for an 800 node cluster, we would need about 128 gigs of space, and we write about 1.3 million rows every day. So this actually reaches a stability period after some time because we start TTL. The TTL starts to kick in, and we don't exponentially start growing. After like a week, it starts to stabilize with respect to the space being used. Okay, so as you saw, there were like 1.3 million records every day. So that brings us to a problem of horizontal scalability. How can we actually scale with respect to cluster size? We should be able to work well with a 5-node cluster as well as a 1,000 node, as well as a 2,000 node, and all that. Also, we should be restart resilient. For example, we have, with respect to Ambari 2.4, whenever a data node sends a metric to AMS, it's a push model. Hence, if something is changed with respect to the API perspective, the data node needs to be restarted to start pushing to the correct format. So we wanted to avoid that from Ambari 2.5. And also, we wanted to cover HA for metrics servers. Heavyweight operations like write needs to be distributed across different collectors we are going to have. And eventually, we want to have an automatic failover whenever one collector goes down. So with these use cases in mind, there were some challenges which we faced. More like, if there were multiple instances of collector running, how do we handle service discovery? And there's always a distributed lock problem. So when we want to aggregate metrics across different instances of collector, how do we make sure we don't do duplication of tasks? And eventually, if one aggregator finishes and writes the checkpoint to a distributed storage, how can the other aggregator picks it up from another host? All these actually led to some investigation as to what we can do with, when we go to a distributed collector story, and we looked at something called Apache Helix. So Apache Helix is a cluster management tool, or actually a cluster management framework, which is used in LinkedIn and Uber production, and it is used for task partitioning and replicas. So this is how Apache Helix works. So you have a cluster with multiple instances where you can distribute the tasks to. So in our case, what is adding a host to an instance is whenever you add a metrics collector, it is an instance, and you add it to your Helix cluster. What is a resource which we want to partition across the different hosts? So in AMS's perspective, aggregators are the most important resource which we want to partition across the instances in the cluster. So we have a host-based aggregation as well as time-based aggregation, which we want to partition across the cluster. We use a simple offline-online model. Basically, if a collector goes down, the aggregation which is supposed to happen in that collector is an offline, so that another metrics collector instance picks it up, and it starts working based on the distributed checkpoint. So at a high level, this is how a multiple collector story will look like. And we have 2 metrics collectors, and each of them are a Helix participant, and each of them have their own aggregated tasks which are responsible for. We are using HBase HA underneath, so the reads can be from any collector, and the writes can be sharded across the collectors. And due to the abstract sync implementation, we are able to make sure that the metric sinks and the metric monitors can seamlessly work with this distributed setup. And both Grafana and Ambari has been changed to work with the multiple collector setup. Okay, so let's talk more about how the write distribution has been done in the sinks and monitors. Okay, so whenever a sink is bootstrapped, it's given an initial set of collectors. And other than that, every collector itself advertises a list of known collectors. For example, if 3 collectors are present in the cluster, each of them will know about every other. The reason why we added this API was because if this is not there, then the sinks might have to talk with Zookeeper. There's already a lot of dependency on Zookeeper, and we wanted to avoid everybody reaching out to the Zookeeper when it knows that the collector is down. So from this set of collectors, we use the host name-based sharding strategy to come up with whatever collector that specific sink is supposed to write to. So this gives us a good distribution of writes. So let's say we have 200 hosts and 2 collectors, and your host will probably be looking like ABC1 to ABC200. We can see good distribution of writes between 100 on one collector and 100 on the other collector. And this collector host, which was got through the sharding strategy, has an expiry interval. So after, let's say, an hour, it's going to expire, and now we might have new collectors in the system, and we can probably do a rehashing it to see if there's some other collector which is more suitable for me. What happens when a collector goes down? So we try for a defined number of failures, and after the failures reaches the threshold, we can use our initial set of collectors we have to come up with a rehashed solution. If no live collector is known from our set of collectors, the final fallback we have is to talk to Zookeeper, and that too we have an exponential backoff strategy, because let's say if you bring down your metrics collector forcefully, not through Ambari, and you have 2,000 sinks, we don't want all 2,000 sinks to be talking to Zookeeper at the same time, so that is going to bring Zookeeper down. So we want to have an exponential backoff strategy to make sure there is no collision. Okay, so we have a number of sinks which writes to AMS collector, starting with Hadoop, HBase, and the newest addition to the metrics collector was Ambari. So going one level deep into the Ambari. So we can now monitor the Ambari performance a lot easier because we have metrics for it. So we have JVM and database metrics. So database metrics are basically Eclipse link, and we have added 2 to 3 Grafana dashboards which give you detailed analysis on what are the different entity tables which are performing good versus bad, what are the queries which are having a lot of cache misses and all that. This is very useful in finding out performance bottlenecks in the Ambari code as well as your cluster. And moving on to the final section, this is the future work in AMS. So right now, AMS is hardwired to talk to HBase and Phoenix. We want to have a story where we tee off the metrics we get to another, it could be an ingestion pipeline like Kafka, or it could be another DB like InfluxDB or Druid. So this integration will be more like a jar-based integration where we'll provide an interface which an external party can inherit from that interface and then give their own jar to us. That's how we want this to work. And so we have seen some scale issues in AMS when it goes past 1,000 nodes, and we are trying to tackle them in multiple ways. The first is the revamped schema using a UUID row key. So as I mentioned before, we have a composite row key starting with the metric name, the app ID, the instance, and also the server time eventually. All these put together, we'll now have the 12 to 16 byte UUID. So this is going to greatly reduce the memory pressure on the HBase mem store, which will actually improve performance a lot. And then the main problem for us at scale is the aggregation. And in the time-based aggregation, or the downsampling, instead of doing it as a collector, we can actually do it as the monitor. So that is what we are working on right now, to have a local aggregator, which is going to run in every host on your cluster. It will do the local aggregation, and it will send the raw data as well as the aggregate data into the metrics collector. So this is going to take a huge task out of AMS. And the cluster aggregation will be done online and on demand rather than trying to aggregate all hosts across all clusters. For example, some metrics like Kafka topology metrics and Storm metrics need not be aggregated across whole hosts. So we want to make that configurable, and we want to make the choice on which metrics we want to aggregate across whole hosts. And eventually, this is where we are going to right now. So we have more than like 10,000 metrics and so many graphs and a lot of dashboards. So the feedback which we get from users is that all this is good when I'm trying to solve a specific problem or trying to look at a specific metric. But can you tell me when my system is wrong, but I'm not able to really see it on my eyes? Is there a way can you find anomalies in my service or in my cluster as a whole? So what we need is actually an anomaly detection system, which we are working on right now. At the high level, these are the requirements which we are focusing. It should be able to target and pinpoint point-in-time anomalies in a real-time stream. It should be able to find out trend and correlation anomalies. So trend could be for a single series, and correlation could be for a set of n metrics which represents a subsystem. And it should be a self-adjusting system because we don't want to have a lot of user input to label the data, whether it's anomalous behavior or not. And then we should have a continuous event processing because that's the only way we can actually give real-time prediction on whether it's anomalous or not. And we want to integrate this with the Ambari alert so that Ambari LS already has a lot of features to talk to emails and SNMP and all that. So we want to use that. And eventually, we want to have a ability to query anomalies, historical anomalies, so that you can use an external system to find how your system is behaving for the last 1 month. Maybe that can be actually used to label the data for future work, and that's what we want to do. So this brings us to the end of the presentation, and questions will definitely be encouraged.
Yeah. So for the Ambari Metrics System. Oh, yeah. There's a mic coming around.
We want to record that.
So the backend database is, you said HBase, and it's an embedded system. So how do you scale the HBase system itself? Because Ambari is running only one node. And so how do you configure to have multiple region servers for HBase to be running on the cluster itself?
Yes, okay. So HBase came in 2 versions with respect to AMS. So the embedded mode is supposed to be for smaller clusters, for more snappier clusters. So we encourage up to 200 nodes. So a single embedded HBase instance is able to handle 200 nodes on your cluster. But if you go beyond that, we definitely recommend something like a distributed node where it's writing to HDFS. And with HA also in perspective, we can have multiple masters and region servers handling the load. So it should not be a problem. Does that answer your question?
Yeah, the HBase cluster itself can go down, right? And that's a single point of failure for the metric system itself.
Yes.
And then as soon as you say the Ambari metric system is going to grow over a period of time, and if you want to keep more of data on the system, then the disk subsystem may not be able to sustain. So you need to have more number of region servers in order to support that. So I don't find a solution with 100, even for 100 nodes. Single node will not be able to sustain those.
Okay. So we have TTL on our tables, so it's not going to grow exponentially, or it's not a linear growth. So up to 1 week it's going to grow, and after which it's going to stabilize. So the maximum data is going to come from precision data, and maximum size is going to come from precision data, and that has a TTL of about 1 week at the maximum. So it's going to drop after that. So that's why we see it never goes past, it does not keep growing over time. It actually stabilizes over time. So that's why we're able to manage with respect to even an embedded mode deployment, we're able to manage up to 200 nodes. And that's what the graph showed with what is your disk space requirement for AMS.
Okay, next question.
With the new version of Ambari, because we have, like when we change some configuration, Ambari recommends some of the changes that the cluster should be having. And also we have smart sense. So I think I raised this question earlier and I just didn't get an answer, but is there any consideration of having just one sort of recommendation rather than having 2 different sets while making these changes?
That's a very good question. So the question is, there's 2 ways to recommend configs today, SmartSense and Ambari itself. Are we going to ever unite those 2 approaches? And that's actually one of our goals for Ambari 3.0. SmartSense uses a Jules engine, and we're actually thinking about today how to split up Ambari Stack Advisor into multiple service advisors and coming up with very cohesive rules that both of those can potentially share. So that's definitely something on the horizon for us.
And the other question is that I was going through the stack upgrade from 2.3.4 to 2.5.3, and it was a rolling upgrade, and it tells you like some sort of warnings, and before the upgrade it tells you need to fix this and that. So the one thing that it didn't complain about it, and I hit the issue, was the Ranger. We had a load balancer.
Okay.
And with the 2.5.3, before the Ranger wasn't using the key tab, but with 2.5.3 it does the key tab integration. So the upgrade took extremely longer time, because when it was trying to talk to Ranger because of the external URL address, it couldn't connect to it, and it was making so many attempts, and so every service restart during the upgrade was taking forever. So is there, I don't know if anyone else reported similar issues, or any thoughts on that?
Not that I know, but we can definitely talk offline on ways to improve that experience for you next time.
Okay. One more question. Any plans to use or actually integrate, instead of just checking the file system size for where the Hadoop is installed, and actually putting all the file system in the node into the alerting system?
are you talking about the different data editors?
Well, actually, because right now Ambari is only monitoring user HTTP where the Hadoop is installed. Now, I'm pretty sure we see that, and a lot of other users see that. You probably get var full or this full, and Ambari doesn't get alerted. And big companies, you have a separate group managing Hadoop and OS. So, instead of admins getting the alert, different group gets the alert for file system full, and then, they call us, so it's just, adds a delay. So, I think it would be good to add all file system on the node into Ambari. I don't think it's a major effort. So, anyone else requested that?
So that's an excellent question, and that really speaks to Ambari's flexibility. You can take the existing alert today for space usage, and either modify it or come up with a new alert based on that to meet your needs, and that's completely acceptable, right? You can come up with custom alerts whenever you want.
I think that's for now. That's all I did. Actually, I updated the Python script,
Yeah.
and I just looked into the mounted file system. So that's how I was kind of managing, but I was just good to have as a little thing.
Correct, and even the development community has thought about an alert wizard that makes it really simple for you to make your own. So because today you have to either add a file and Ambari has to restart to pick it up, so it's definitely a good idea. Okay, one more question?
Any plans of having one Ambari instance managing more than one Hadoop cluster?
That's a very, very good question. So managing multiple Hadoop clusters. There's multiple ways of going around this, and it really depends on what you really want to accomplish with multiple clusters. It's definitely not a possibility we would rule out, but I guess we can talk about it offline.
I thought that's possible through views, actually. You can add URL for the other cluster.
So you can definitely do data replication or this CP, but I think you're referring to having a single Ambari have a very top level view of multiple clusters, right? Like
Manage one cluster.
You can do it. That's what I'm saying. If you go to Ambari views,
mhm.
you can add another Ambari cluster. Try that. Go Ambari views.
If you're referring to have Ambari have deeper knowledge of multiple clusters, each configs, like dev staging prod environment and replicate those things, that's something we can talk about as a future feature. I mean, there's a lot of work in Ambari 3.0 for enabling a lot of use cases around, you need, for example, if you want your own Zookeeper instance with its own Kafka and Storm, yet you want another instance of those same things for a different workload, perhaps also use Spark, right? Different versions. So we're going to talk about that in Ambari 3.0. It's not exactly multiple clusters at this point in our discussion, but it is multiple services and multiple instances.
And the other weird thing that I noticed, like when you have a Ambari user, right, you try to change the password, there is no option. So, what you have to do is probably you have to delete the user and recreate the user. So, that's something that definitely needs to be on the piece. I don't know if I mentioned that.
Yeah. So the question is making it easier to change your password as a user.
Because right now, what I have to do if someone forgot their password, even me as an admin, I cannot change the password for a user.
Mhm.
I have to delete the user, re-add it, and then, grant privileges for all the views.
I see.
That's, I think that needs to be, if we can get that, that would be great.
Yeah, we could definitely take that as an enhancement or something we can look at.
Okay, gentlemen, thank you.
Okay, thank you everyone for having
We're
us
going to
today.
take a short break, and then the next session.